Welcome everybody to lecture 10 of information theory. This is a YouTube only lecture, so it's possible that my sound quality will sound very different. And this is always a little bit strange for me because I'm just talking to a computer who doesn't talk back to me or ask any questions and doesn't laugh at any jokes. So I don't get any feedback at all, but I'm just going to pretend that I'm in front of all of you and everybody is enjoying everything that I say. So let's get started. So like I said, this is lecture 10, and this is actually going to be placed on YouTube on Monday, the 28th. So a couple of announcements. Well, this is lecture 10. Actually, this schedule is a little bit messed up. What is definitely still true about this schedule is that on the 31st we will have a midterm, and I will be talking about that on Tuesday during our 1 hour of lecture on Tuesday, from which I will talk about in 1 minute. So here's our cumulative reading. This hasn't changed since last lecture. You should really know this stuff at this point. The midterm will include all of this reading. Also, homework is due Tuesday the 29th. This is our last homework before the midterm. And of course we'll get the it's going to be a hard deadline in terms of the lates, because I want to try to get this, I want to get the, actually not try, but I want to actually get the solutions to this homework up on the web page maybe by midnight, or 1 a.m. Wednesday morning. So just a couple of more announcements. Well, there's of course office hours on Tuesdays. God, I still haven't fixed this typo. You know, I fixed so many typos of these lectures. I haven't fixed this one. Also, Tuesday night I'll open up a Canvas office hours. We have a midterm in class. Again, I wanted to mention that this is pretty cool. So Stephen Boyd, whose lectures are much better than mine, and he tells much better jokes than I do. So we are actually, his jokes are so good that we're only going to do a 1 hour lecture on Tuesday, which is the reason for this YouTube video. So I'm going to do a 1 hour lecture on Tuesday from 2:30 to 3:30, and then and that's going to be in EEB026. So this is our room for Tuesday from 2:30 to 3:30. So don't come up to Packard. It's this room right here. You cannot say that I'm not telling you. It's 026. Okay. I won't be in our Packard room. I will be in 026. And what we'll do is we'll meet from there's a typo here, a pretty silly one. 2:30 to 3:20. And then after that we'll walk right over to the Boyd talk. At least you guys will. I will probably spend the next 7 minutes disassembling my ridiculously elaborate video recording system. And then I'll walk over to Stephen Boyd's talk. That will probably be pretty full, but I want you guys to see it. Okay, so now on the midterm, this is stuff that we talked about last time. The critical thing that you should be starting is one 8.5 by 11 inch sheet of paper. You might want to start on that now, or hopefully maybe you've even finished it. But that's basically the main thing I wanted to remind you about here. So this is a quick review of what we talked about last time. So there was Kraft's inequality, which basically says that if we sum over all code words, and it takes an alphabet of size d, and we take d to the negative length, and that's going to be no greater than 1. And the critical thing that this gave us was that it connects the code existence to a mathematical property on the lengths, and then given these lengths, we can construct an instantaneous code, as we will see. And in fact, at this point, we've now seen that. We've seen that construction. We could actually think of finding the optimal integer codes as this optimization problem. Today we're going to talk about Huffman, which actually tells us how to compute this. Now, this doesn't mean that integer programming is, in general, always possible to solve, but sometimes it is, and sometimes it isn't. In this particular case, it is, as we will see. What we saw last time is if we did a relaxation of this integer optimization problem and turned it into a Lagrangian and did a relaxation to real values, that the optimal real valued code word length was the information about the events. So this was a pretty fundamental discovery, because this is saying that our notion of information that we discussed in the first lecture was the optimal length. And in fact, this means that when we actually have any real lengths, that it has to be worse than this. So basically the entropy is a lower bound on the true coding length for any of these symbol codes. Another definition here, we talked about d-adic distributions. Like here's a d-adic distribution. Basically the probabilities have to be 2 to the negative some integer. That's what d-adic means again. We also, the point of this slide here is again is to say that these are the Shannon codes, and it uses this as the length. Basically what it does is it takes the information log of 1 over pi, but then it rounds it up to the next integer by taking this ceil function. And that ends up being the Shannon length, and here's the length right there. Okay. Right, and then just to remind everybody also, this line says that Kraft inequality holds for these lengths. So basically what it's saying is that these lengths are such that there exist instantaneous codes. So we can just do these lengths and we're guaranteed to have an instantaneous code. We talked about the efficiency and how the Shannon codes led us to 1 bit per symbol of penalty. The question is how bad the overhead is. Well, it depends entirely on the entropy. For low entropies, this is pretty bad. For high entropies, it's actually pretty good. And if the entropy gets really, really large, then this is not bad at all. And that's essentially the whole idea of block coding. When we do block coding, we essentially make effectively that entropy big enough such that that additional bit penalty per symbol. Now this is, in this case, it's a block symbol. It basically means that the bit penalty per original symbol goes to 0 as 1 over n. And so basically we take this, divide by n, let n go to 0, and I can't remember if I added that. Yeah, so what happens is that when we divide everything by n to get the per symbol code, this part here, the 1 over n goes to 0 as n gets big. And I think this is one of the last things we talked about, is just if you code with the wrong distribution, like for example, let's say you do Shannon codes, but you use Q, which is the wrong distribution, and then P, then basically we pay a penalty of the Kullback-Leibler divergence between P and Q, which is this. So basically, even in the best of cases, the lower bound is the entropy, which was the original lower bound when P is equal to Q, and this is equal to 0. But when it's not equal to 0, we pay that as a penalty. Okay. So, oh yeah, the last thing is that we showed that Kraft was true not only for uniquely decodable codes, not only for instantaneous codes, but it was also true for any uniquely decodable code. And so basically this said that there's no benefit, there's no better code in the space of uniquely decodable codes than there is in the space of instantaneous codes. Instantaneous codes is smaller, but it has this other property, which is that it's easy to decode. And so therefore we should never bother going to the uniquely decodable code that's not instantaneous. Okay. Now I think we saw a couple of these slides. We're going to start the Huffman section now. So what Huffman says is that, well, the question is Shannon's code optimal? And so we start with x, which is a binary symbol, and let's say that these probabilities exist. So one probability is much, much larger than the other. Like one probability, the probability of x being 0 is 10 to the negative 1,000th. And so the Shannon lengths we saw were that since that guy is improbable, Shannon would assign a very, very, well, I should say the Shannon code would assign a very, very long and silly length and for that guy. And this guy would get a good length. But the whole point is that this is a silly length. You don't need to ever have a code where that's that length. I mean, it's a binary. The symbols are binary in the first place, so you should use it's already in bit form. So we're using way too many bits. And in general, I mean that's kind of a silly example, but in general, Shannon codes can be longer than necessary. And so what we want to do is try to come up with, well, Shannon basically is not an optimal integer length for a prefix code. So what we want to do is come up with a procedure for finding the shortest expected length of the prefix code. And Huffman, believe it or not, does that. It's an interesting algorithmic procedure. It's not in some sense mathematical in the sense that we write equation. We actually have to run an algorithm to do it. So as a result, it's a little bit harder to analyze mathematically. And that's what we'll be doing today. So we're going to look at it in terms of the tools of information theory. So again, the quest is, given some probability distribution, find a code, which is bit strings for every possible source symbol, and each bit string is of some length, and that should be as short as possible, and it also needs to be prefix free. Now, we're going to talk about this idea of a greedy algorithm, where we sort of start at the top and we split the potential code words into even probabilities. And why do we want even probabilities? We'll talk about that in a minute, because it corresponds to the greatest entropy reduction, the greatest uncertainty reduction. But basically, we want to ask the question with the highest entropy. Now, that might not make sense at first, but I hope that in the next couple of slides, I will convince you why asking the question with the highest entropy makes sense. Now, it may not be optimal, but it does make sense, as we'll see in a minute. Now, it turns out that this is very similar to the game of 20 questions that we saw before. We have a set of objects, and without loss of generality, let's assume that the set of objects corresponds to the integers 1 through m, and that these occur with probabilities that are proportional to these weights, these non-negative weights, w1 through wm. Okay. And we want to determine an object from this class asking as few questions as possible. And the questions can take the form, is x in the set A? So really what's happening, as I will say a couple of times, the question is determined by the set A. So A is some subset of S, right? And S, remember, is this set of integers. So we just choose a subset of S, and then we ask, is it in this set? Then we choose another subset. Is it in this set? Then we choose another subset. Is it in this set? And we can choose any subset we want. And each one of them corresponds to a yes-no. Well, each one of them is a yes-no question. And the answers are yes or no, and that corresponds to a binary code, because the string of yeses and nos corresponds to the strings of ones and zeros. So here's an example. We've got a question tree. In this question tree, the first question is x in this set, x2, x3? And if the answer is yes, then the next question is x equal to x2? And if the answer is yes, then we have our answer, which is that x is equal to x2, and that corresponds to that probability. On the other hand, going all the way back to the top, if the answer is no to this original question, then it doesn't make sense to ask, is x equal to x2, because we already know it's not we know it's not, since the answer to no is no, we know it's not x2 nor is it x3, so it can't be either of them. So we start asking questions about the remainder. We've in some sense eliminated x2 and x3, and the remainder is either x1, x2, x1, x4, or x5. Okay. So now let's say we ask is x equal to x1, and if the answer is yes, then this becomes the final answer. Alternatively, if the answer to that question is no, then we ask if it's equal to x4, and if the answer is yes, then of course then the answer is finally that it's equal to x4, and otherwise the answer is no, and then the answer is x5. And so the corresponding probabilities, these are the final answers. x2 with probability 0.2, x3 with probability 0.2, and so on and so forth. And so this string of bits, the code for x2 becomes yes, yes. The code for x3 becomes yes, no. The code for, say, x5 becomes no, no, no. Okay? So, how do we construct such a tree is really the question, because this, we want it to be such that it has the shortest possible length. This length, this no, 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 has probability 0.15. And we essentially look at these lengths, from root to leaf of the tree, and multiply by the probability, and then we multiply by all the probabilities and all the paths from the root to the leaves, and that becomes the expected length. Now here's a quote from Charles Sanders Peirce in 1901, and he in some sense had the right idea of the following. Thus 20 skillful hypotheses will ascertain what 200,000 stupid ones might fail to do. The secret of the business lies in the caution which breaks a hypothesis up into its smallest logical components and only risks one of them at a time. So in some sense, what he's saying is that we ask useful questions, 20 skillful hypotheses, and if we ask useful questions, then that will give us the same information as what 200,000 poor questions. Now, useful, skillful hypotheses, what we'll see, will correspond to those with high entropy. And the greedy algorithm, so now the greedy algorithm, both the greedy algorithm and Huffman will do that. At the top of the tree, in general, high entropy questions will be asked. But the greedy algorithm basically sort of has this flavor to it. The greedy algorithm is sort of a class of algorithms that says, do next whatever currently looks best, irregardless of what the future may hold. And that is worth writing down, maybe. Irregardless of what the future. That sounds like a very philosophical, poetic description of the greedy algorithm. However, that in some senses, well, not in all senses, is correct. So here's how we will introduce this algorithm. We have a set of probabilities and a set of symbols, A through G. And the table gives the probabilities of each symbol. Like, for example, the probability of C is 0.05. Okay. Now, the question that looks best would infer the most about the distribution, and that corresponds to the one with the largest entropy. So how does that work? Well, it's the one that reduces the entropy the most. So we've got the original entropy, the entropy of X, and we've got the conditional entropy, which is this. And the conditional entropy, as we know, is equal to this, the joint entropy minus the entropy of the question. Now this joint entropy here, so once we know X, Y is determined, right? Because Y is just a function of X. So it turns out that the entropy of this joint is just equal to the entropy of X. So then we therefore get that this whole expression becomes just the entropy of X minus the entropy of Y. And so if we choose a question Y that has large entropy, it leads to the least residual uncertainty, where this is the residual uncertainty about X. So choosing a question with large entropy does that. And the least residual uncertainty means that we know the most about X because the uncertainty about X has been diminished the most. Now another way of looking at this is we can choose the question Y with the greatest mutual information about X. And why? Well, h of X is a constant. So we look at the mutual information between the question and X, and that's defined based on this thing. But then if we just use the definition that we did above, then that's just equal to h of Y. So it turns out the entropy of Y is identical to the mutual information between Y and X. In this case, it's Y1. So we want to find questions with big entropy. Now again, how do we decide what questions? It's all about the set A. Choosing a subset is what determines the question. All of the questions have the same form, and they're all parameterized by the set A. So that's what we've got to do. So what we'll do is use greedy and choose the questions with the greatest entropy. So let's consider we've got this set A through G, and we partition this question in half, or well, I guess in probabilistic half, A through D and E through G. And so the question then becomes, is X in this set E, F, G? Now that question has maximum entropy because the answer, it's binary, it's either yes or no. If it's yes, then the probability of yes is 0.5, and if it's no, the probability of no, it's also 0.5. So that question has probability 0.5 of being yes or no. And so for all binary questions, that question has entropy 1. It's the maximum entropy. It's as good as it gets. It's the best, it's the highest possible entropy question we could ask. Now that doesn't mean it's the only high entropy question. There could be other questions that have entropy 1. But the greedy algorithm says, well, that's all I'm going to do. I'm going to look at the different questions and choose the one that looks best, regardless of what happens into the future, or whatever that quote was I wrote down before. So now the next question that we ask depends on the outcome of the first question. So we have two possible outcomes, either y1 is equal to 0, in which case that means that the remaining uncertainty lies in the set of variables a, b, c, d, or alternatively, the answer to the question was yes, and the remaining uncertainty lies with x being e, f, g. Okay, two possibilities, and what we're going to do is recursively decompose each one. So let's consider first the case when y1 is equal to 0. Okay, so then what we want to do is split the remaining choices and ask a question about the split. So that has maximum entropy. Now if we look at the set A, B, C, and we split it into A, B, and C, D, those have equal probability. The probability of A, B, and the probability of C, D is both 1/4. And out of the remaining choices, conditioned on A, B, and C, D being true, those choices have probability 0.5. And so therefore it has highest entropy. I guess another way of writing this would be to say that if we look at the probability of the set A, B given the set A, B, C, D is equal to the probability of C, D given A, B, C, D, which is equal to 0.5. So the conditioning event turns it into a 0.5. Now, just in case this is clear, what we really mean here in each of these cases is, this is the probability of x in this set given that x is in this set. Okay, and same for this other guy down here. But you get the idea, hopefully. And if not, you can rewind and listen to this again. So that's as good as it gets, again. So now let's split this question. Let's assume that the first question's answer is 1. And so if the answer is 1, then we need to split this set, E, F, G. Now, this is not as easy as splitting it down in the middle because there's 3 choices, 1, 2, or 3, where we either split it E and F, G, or E, F, and G, or E, G, and F. And the corresponding probabilities are here, and corresponding entropies are here. And we just compute these, and the greatest entropy 1, so given that y1 is equal to 1, what's the residual entropy of y2? That corresponds to this guy. So that guy, split number 1, has the highest entropy, so we choose that. So that reduces the entropy the most. And again, so now we have 2 questions, y1 and y2. So we have the entropy of x given y2 and y1, which is just by the chain rule, entropy of x given y2 and y1 minus the entropy of y2 given y1. And then if we do the same thing again, we have the entropy of x given y1, which is entropy of y2 given y1, which, as we know, is the entropy of x minus the entropy of y2 given y1 minus the entropy of y1. So each one of these questions we ask, like we first ask entropy of y1, which removes some of the entropy. Then given y1, this guy removes some of the entropy. And maybe there's some residual uncertainty. But once we've asked these questions, like if we ask another question, y3, and if y3 given y1 and y2 are such that that when we subtract all of those question entropies from h of x, we get 0, we'll know the answer because we will have reduced the entropy down to 0. Residual entropy adds up to the total entropy. So in general, once we ask the first and second question, we get down to sets only of size 2, and there's only one possible question in that case. So there's no choice. So let's summarize all the splits in this following table. So the first split is this guy. Let's make it a little bit thinner, I guess. This first split is this guy. Which is the entropy of y1. The next split is this one. In the case that y1 is equal to 0, the next one is this one. In the case that y1 was 1. And then we do all these other examples, which I'm not going to talk about. But these are the corresponding splits. These are conditionings, and what's shown here on the right, this is showing the entropies. Okay. Now let's add it up. Now these are, by the way, conditional entropies conditioning on each one of these events. These things that we're conditioning here, we're conditioning on y2 is equal to 0, y1 is equal to 0, y2 is equal to 1, y1 is equal to 0, y2 is equal to 0, y1 is equal to 1, and y2 is equal to 1, y1 is equal to 1. So all of those things are specific values of y. Those things have probabilities, and to actually compute the entropy, we need to essentially sum over that. So let's first of all recall that, or realize that h of x is 1.9323, and that turns out to be the entropy of these three questions. So that means that it must be the case that when we look at these three questions, we've determined everything. And that, of course, makes sense because by the time we get down to the third question, there's only a choice of 2 at most. And we ask a question, is it one of those guys? And then we get the answer, and then we know what the final x is. So then to break down this entropy, we just do what we know. This is the chain rule. This is the entropy of y1. This is y2 given y1. This is y3 given y1 and y2, in which case we have to sum over all possible outcomes of y1 and y2. That last term. So here's what we get. We get this tree. Let's zoom in on this a little bit. So at the beginning, we have everything. We ask the first question, is it in EF, or is it EFG, or is it in ABCD? That happens with 0.5. Here's this other question, is it in AB, or is it in, maybe I should be using yellow for all of this. Is it here? And then now we're left with one question each, so it's either going to be A or B, and then when it's this question, it's either going to be C or D. And then similarly, we go down. We go down this way, and on this path, there's only one remaining set of size 2 left, and so we ask the question, either it's F or it's G. I didn't actually, in this bottom row, I didn't actually list it as a question because we just ask one question. It could either be A or B, and we'd get the same answer. But the point is that we also, now let's erase all this stuff. We also have these other things, these bits. So if we went down this path and this path and this path, we have a code 0, 0, 0. If on the other hand we went down this and this and this, we have a code 0 and 1. And each path from the root to a leaf has a bit pattern corresponding to the leaf, and that becomes the code for that case. So notice that every code except for this one is of length 3. It's only one code of length 2. Okay. The expected length of this code is 2.530. The entropy is 1.9323, as we said. And now, is that a good code? The overall efficiency is 0.7638. That probably is not a good code. And the question is, can we do better? And that's what we would like. And let's construct the Huffman tree. In fact, let's look at the greedy tree. And the Huffman is also going to build a tree, but the Huffman tree is going to look very, very different. Now, what's interesting, first of all, is when you look at the top. The greedy tree split it at 0.5 and 0.5. So that was the maximum entropy. That was greedy. It turned out that, remember, greedy is do next whatever looks best, irrespective of future consequences. And the problem was that when we did that, we thought, greedy thinks, oh, we've got this perfect question which has entropy of 1, but then it turns out that you can't change that decision. You have to live with it, and you suffer later, and you get a very sort of long code word for each one of these things, including, this guy. Like, look at this guy. It's something that happens with probability 0.47, and you've got a code word that has a length 2. What the Huffman tree does is that that guy's happened so probably. Let's just give him a code word length of 1. Okay, and the first question doesn't have maximum entropy. It's not bad. I mean, it's the split between 0.47 and 0.5. That's pretty high entropy, but it's not going to be entropy of 1. And notice also that the Huffman tree is very imbalanced, right? But let's take a look at it. This is about evenly split. This is not that evenly split. This is pretty evenly split. This is evenly split, and this is evenly split. So there's really one non-evenly split guy, but the tree ends up becoming very imbalanced. And let's look at the expected lengths. The Huffman expected lengths expected length is 1.97, which is much, much smaller than the greedy, and the efficiency here is 0.9809, which is not bad. So the greedy procedure, clearly, this is an example showing that greedy splitting, greedy question answering is not the right way. And you could sort of take this as a rule of life, that you shouldn't be greedy. You should sort of think through your decisions from maybe the final conclusion on back to the present, rather than sort of doing next whatever looks best at the moment. So why does starting from the top and splitting be non-optimal? I mean, basically the issue is in general, I mean, splitting high entropy things are useful, but there are many different ways of splitting at roughly 50%, or entropy is equal to 1. And if you take the wrong one, that decision is irrevocable. You can't change it later on. So you're sort of stuck with a decision, and maybe a decision that's a little bit lower entropy but leads to much better future consequences is better, and that's what we saw exactly. So the Huffman code tree procedure, what is as follows. Here's what Huffman does. So you take the 2 least probable symbols in the alphabet. These 2 will be given the longest code words. They will have the longest code words, and they will have equal length. And they will differ in the last digit. And we combine these 2 symbols into a joint symbol having probability equal to the sum. This will make sense in a second if it's not clear, because I'm going to give you an example. And then this new joint symbol, we're going to remove the old guys and add the new one, and then we're going to just repeat. Just do this iteratively. So the two old symbols are going to become that were least probable are going to become a new symbol, and then we're just going to repeat this whole thing. So note that it's bottom up. In some sense, it's agglomerative clustering, and rather than top down, which is the greedy procedure. So it's a very different strategy for constructing. So here's an example. So we've got 1, 2, 3, 4, 5 as the alphabet, and these are the probabilities: 1/4, 1/4, 1/5, 3/20, and 3/20. So we start with the least probable ones, which are the 2 symbols with probability 3/20 and 3/20, and those happen to be 4, 5. And so we're going to build this from left to right. So basically, this is the bottom. This is going to be the bottom of the tree here, and the top of the tree is going to be here. So the tree is going to sort of expand this way, as you will see. But right now, we're at the bottom of the tree on the left here. And all we have at this point is just essentially the symbols, 1, 2, 3, 4, 5, and the corresponding probabilities. We take the 2 least probable ones, the 0.15 ones, and we merge them giving binary patterns 0 and 1. And merge symbols. So we have some merge symbols. So this guy, this 0.3 here, corresponds to a merge symbol, but we don't even need to necessarily give that a name. We just sort of implicitly give it a name. It's merged 4, 5. If you want, you could give it 4 or 5, which doesn't mean 45. It just means the merge symbol 4 concatenated with 5. And then now we've got a new set of probabilities. We find the two least probable ones. And does anyone wish to care to recognize what they are? Well, it doesn't matter. There's different choices. So let's just take these two. Let's take 0.25 and 0.2 and merge those guys, like again giving them a bit pattern or a bit associated with that, and that's going to give us probabilities 0.25, 0.45, and 0.3. And we take the two least probable ones again, which are 0.25 and 0.3, merge them, give them bit patterns, and we get 0.55. And then lastly, there's no choice, we just have two bit patterns, 0.55 and 0.54. And we merge them. So going down from the top, so the top is 1, it's got all the probability. The first question is got entropy, it's not entropy 1, but it's these probabilities are close to 0.5. Not so bad. The next one is also relatively close. I mean, it's not perfect. It's 0.25 and 0.33. The next one is also relatively close. The next one's also relatively close. But it's not, again, it's not necessarily exactly equal to the entropy of 1 in each case. This last one is, it turns out. So we have the expected length is equal to 2.3 bits. The entropy is equal to 2.2855 bits, and this code does pretty well. It's pretty close to optimal. Now, one thing to note is that some code lengths are shorter and some code lengths are longer than the Shannon lengths. The Shannon lengths are these things. Actually, these aren't the Shannon lengths. These are the optimal lengths, and some optimal non-integral lengths. And some lengths are shorter and some lengths are longer. The construction is identical if we have a non-binary alphabet. So now here are the Shannon lengths. The Shannon lengths are the seal, and they're not optimal. And we also saw the example when we had this tiny little probability. Maybe a more realistic example of a binary case is like when maybe P of A, we have two symbols A and B, and P of A is equal to 0.9999, and P of B is equal to 1 minus 0.9999. There's 4 nines there, and it leads to lengths 1, the probable one, and 14. So that's not as bad as before, but it's still not so great. And the expected length is going to be this, which is greater than 1. Now, Huffman, of course, in this case would be optimal. It would give you an expected length of 1 because it does bottom up. The optimal code lengths are not necessarily always less than this, however. Here's the Shannon length, and it turns out that there will be times when the optimal code length is longer than the Shannon length, but not on average. And here's an example. So consider X. This is with probabilities 1/3, 1/3, 1/4, and 4/12. This has entropy 1.8554. The Huffman lengths can be either, there's two choices here when you're doing the Huffman length. They can either be 2, 2, 2, and 2, or 1, 2, 3, and 3. And it's an exercise to show that. But if we look at the Shannon lengths, log of 1 over P3, which is equal to this, is equal to 2. And that actually ends up being less than 3 here, which is one of these, which is, I guess, this 3. The Shannon lengths are 2, 2, 2, 4. And the expected length is 2.1557, which is greater than 2. And certainly greater than the entropy. So, a particular code word for the optimal code might be longer than the Shannon's length, but obviously if it's an optimal code, on average it's going to have a shorter average length. Now it turns out that Huffman is optimal, which is which is remarkable and surprising and great. That basically means that amongst all codes with integral lengths, this value is minimum. That's the expected length. So to show this, basically what we're going to do is we're going to show a lemma that says that some optimal codes have certain properties, but not all. Some. And that there exists a code with these properties. Next, what we're going to do is we're going to, in some sense, be given a code CM. This is going to be a sort of an interesting recursive proof. We're going to start with a code CM for M symbols that has the above mentioned properties. And we're going to do a little manipulation to produce a new simpler code satisfying the lemma that's simpler to optimize. And then we keep doing this recursively. And then we get down to a code that in some sense has been constructed most of the way through the proof, except that once we get to the final code that involves optimization, it becomes trivial. It becomes essentially just assigning one bit to each code word because it's a size 2 code. And the proof essentially means that you're guaranteed to, when you get to the end, have a very, very simple problem to optimize. So, here's the theorem we need to show. This is going to be a little involved, and you're welcome to rewind this multiple times if you want to. Can't do this in class. So what this is saying is that for all probability distributions, there exists an optimal instantaneous code. Remember, this is prefix free. An optimal means it's got minimal expected length. And so there is some code that satisfies the following three things. Number one, if you take two probabilities, Pj and Pk, and where Pj is the greater, strictly greater, this is strictly greater than Pk, then the length for j is no greater than the length for k. So in other words, there exists a code where when you take a more probable symbol, its code word length is no greater than the less probable symbol. Second property is that the two longest code words, so now these properties are satisfied simultaneously. Satisfying, what we mean is like, this theorem means it's satisfying 1, 2, and 3 at the same time. Satisfying simultaneously, maybe I should add the word here. Simultaneously. Let me do it a little bit smaller ink here. Simultaneously satisfying property 1. Property 2 is that the two longest code words have the same length, and property 3 says that the longest code words differ only in the last bit, and correspond to the two least likely symbols. Okay, so how do we prove this? Let's start with property 1. Suppose CM is optimal. So CM is what's given, it's optimal. And so that means that the length, expected length, is going to be minimum, which is this. And just choose two probabilities where Pj is greater than Pk. Okay, so we're just going to choose some arbitrary Jk, and this is the assumption. So basically, property 1 is saying if Pj is greater than Pk, then Lj is less than Lk. And what we need to show is that there exists a code such that this is true. Let me fix this actually for a second here. This should say, show that there exists code with. Okay, now let's consider a new code, C prime, with code words j and k swapped. So what we're going to do is, it's the same probability, but we're going to swap code words j and k. So that means that in code, everything's going to be the same in code C prime, except that the Ljth code word is going to get in the new code is going to take the length of the Ljth code word is going to, in the new code, is going to be the same as the length of the kth code word in the old code, and similarly with k and j here. Now this will only make the code longer. And why is it? Because essentially the expected code longer, so it's going to make this L of C prime going to be greater than L of C. And the reason for that is because what we're doing is we're giving a more probable code word a longer length, or at least, and then we're giving a less probable code word a shorter length. Okay. Now, let's look at the next slide. So what this is going to do is basically the following. Wait, well, before I actually say that, let me make sure I'm clear about why this code gets longer. The reason is because we are assuming that L is minimum. So this code is optimal. So it has to have the shortest possible expected length. So anything we do to that code has to make it longer. This is the optimal one. And anything we do to it, no matter what it is, makes it bigger. Or at least not strictly, but it's certainly not going to get shorter, because otherwise our assumption that C prime is optimal would be false. Okay. Now with this swap, we have 0 is greater than or equal to this, and this basically comes from the optimality of C. And here's just the definitions of the expected lengths. Now most of these guys, except for J and K, are going to be the same. So most of the stuff is going to cancel out except for the J and the K. Now in this code, in the new code, the stuff that doesn't cancel out is PJ LJ prime and PK LK prime. In the old code, this is the stuff that doesn't cancel out. So now let's plug in the old value. So remember, the reason why this works is because LJ prime is the same as LK, and LK prime is the same as LJ, and everything else is the same. So we can just do that substitution. And now the rest is just a little bit of algebra and a little bit more algebra. Now we've got this quantity in equation 10.8, which is, this whole thing is guaranteed, thanks to the optimality of the code, to be greater than 0. So this product down here is guaranteed to be greater than 0. Now this guy here, PJ minus PK, we based on assumption, we chose PJ and PK such that PJ is strictly greater than PK. And so therefore that's going to be greater than 0 too. So we've got this is greater than 0, this is greater than 0, so two things that are greater than 0. So it must mean that this guy here must also be greater than 0, greater than or equal to 0. Because otherwise we wouldn't have this whole thing being greater than or equal to 0. If that guy was negative, we would be negative. So therefore, whenever it's the case that PJ is greater than PK, we must have that LK is greater than or equal to LJ. And the code satisfies property 1. And in fact, we've proven something a little bit stronger than the there exists property. We've chosen that all optimal codes have this property. So all optimal codes have the property that if one symbol is more probable than the other one, the more probable one and the less probable one must be such that the less probable one can't have a shorter code word, because if it did, you would violate the optimality, because you would always swap and make the code shorter, expected length shorter. Okay, so let's talk about property 2. Basically, the longest code words have the same length. So if the two longest code words are not the same length, then we can actually delete the last bit of the longer one. And the reason why we can do this is because it's a prefix code, and by doing this deletion, we retrain the prefix property. The longest code word is unique in its length. Everybody's not nobody's a prefix of anybody else. And so when we delete the last bit, we retain this prefix property. Here's some pictures that show it. And we could get rid of that red bit and we'd still be prefixed, because basically nobody's a prefix of anybody else. The second longest is not going to be prefixed. So in doing so, we've reduced the expected length. And so therefore, in the optimal code, the longest code words have the same length. So the optimal code, in fact, we've proven that the optimal code must have the two longest code words of the same length. Otherwise, it's not optimal, again in the prefix condition. Now the last property is that the two longest code words differ only in the last bit and correspond to the two least likely source symbols. Now property 1 says that gives us the least likely part. So basically, remember, here's property 1 again for your convenience. And let's say that if pk happens to be the smallest probability, then it must have a code word that's length that's no less than any other more probable one, j. And similarly, if pk is the second least probable, then it has a code word length also in some sense no less than any more probable one. So the two longest code words have the same length and correspond to the two least likely source symbols. And let's say we need them to differ only in the last bit, which basically means that they're siblings. They're both leafs that are siblings right at the node right above the leaf. Then if they're not siblings, we can essentially do this transformation where, maybe there are a couple of other guys, but we can just sort of swap them. We can sort of swap, maybe they lie here and here, we can just swap them so that the two least likely ones. So this property 3 is not like a necessary property. This is basically just saying there exists a code that's optimal. It's a prefix-free code that has this property. So it's saying that insisting upon this property doesn't mean we leave the space of optimality. Now, any of these sort of changes that we do, like for example doing the swap, doesn't change the length because we've kept the same length of the two least probable symbols, so the length is the same. Okay, so we've now proven the 3 properties, that there exists a code with these 3 properties. So if these probabilities are sorted in this way, so PM is the least probable and P1 is the most probable, then there exists a code that has these lengths. The LM is equal to L. These two lengths, LM minus 1 and LM, are the lengths corresponding to the two least probable values, and where the code word for XM minus 1 and XM differ only in the last bit. So what we're going to do next then is demonstrate how the Huffman procedure is optimal by starting with a code, and then we're going to produce a new code based on essentially what the Huffman operation does, and where the optimization of the original code is dependent. When we want to find the actual length of the original code, we actually sort of boil it down to optimizing it over a code with fewer symbols, fewer symbols. And this might sound like it's impossible, but in fact it's really showing that the Huffman procedure preserves optimality down until we get to essentially a code for symbols of size 2, in which case it's obvious how to find the optimal. You just assign 1 bit each. And meaning you don't assign more bits than necessary. And then the Huffman code preserves the optimality along the way. And the optimal code will be apparent. So let's assume that we've got some not necessarily optimal code, some code CMM, and we've got M symbols, and it satisfies all of the above properties. Okay, the properties 3, 1, and these are the code words: omega I for I is equal to 1 to M. With the Huffman procedure is going to turn essentially CM into a code for CM M minus 1 with these code words. We're going to have 1 fewer source symbols and 1 fewer code words. Okay. So here are the original code words. We've got M of them. Here are the corresponding lengths, and here are the probabilities. And again, we're assuming that PM minus 1 and PM, these are the least probable ones. Okay. Now what Huffman's going to do is build this tree backwards, taking the 2 least probable ones and giving them a bit, 0 or 1, and then in some sense merging those guys and then sort of creating a new guy with those guys merged, and with the only condition that the code words for that for the ones that just got merged correspond to the code word for whatever the merged guy was with an appended 0 or 1 onto it. And that's exactly what this is showing. You've got the original probabilities, you've got the original size m lengths, and now this is just writing them in terms of the size m minus 1 lengths, and now but we've got the m minus first length here and here being whatever L prime m minus 1 is plus 1, and that corresponds to appending this 0. So here's an appending of 0 and a 1 onto the merged code word. This is the code word for the merged symbol that came from merging Wm minus 1 and Wm, which are the two least probable code words. Everything else up here, all this stuff stays the same. So in fact, this whole table in some sense is the same. The only thing that in some sense happens is that we create a code word here corresponding to these two code words. And then we add, like a 0 and a 1 on here to create this. Now, this is where it gets a little bit interesting. So the Wi are the Cm lengths, and the Wi prime are the Cm minus 1 lengths. Okay. And the lengths, in some sense, we define them implicitly and recursively. We don't really know what the lengths are. All we know is that whatever the lengths are, the symbols that we've merged have lengths 1 more than the length of whatever is going to be given to the merged symbol that we've created. So Huffman is kind of lazy in that way. It's not greedy, it's lazy. It basically says, well, I'm going to do the least amount of work, and just going to say, well, I'm going to take these two least probable guys, and I'm going to assign the n bits as 0 and 1, create a merge guy, and then let my recursive Huff version of myself finish. So what we get is the following. Here's the length of Cm, which is just the expected length. Now this is equal to, we're summing over the first m minus 2 symbols here, and we're just breaking it out into the m minus 1 case and the m case. And we're writing it now this in terms of the lengths of the new code, L prime. Now for m is equal to 1 through m minus 2, this Li prime is equal to Li. So we've just renamed these guys. Here, these guys is equal to L m minus 1, and this length is equal to Lm. That's what Huffman does, right? Those are the non-primed lengths. And the corresponding probabilities, which is this and this. Now we rearrange a little bit. We've got now, this is going from equation 10 to 11 is just a little bit of algebra. And we now have a merged probability for this merged symbol, or an added probability for the merged symbol. This is the length of the merged symbol. And what we're left with is these two probabilities, which sort of stay out. Now, what's interesting about this is that when we do this, when I say stay out, we've got a new thing to optimize over. So we've taken the original problem here, which involved L lengths. We've turned it into a problem with, the problem here with M lengths. And we've turned it into a problem with M minus 1 length. M minus 1 lengths. And these probabilities are constant with respect to the lengths that we want to optimize. In this case, the M minus 1 lengths. And so these guys become constant. They don't actually hurt or make any more difficult the optimization procedure. So that constant doesn't involve the lengths. So we've reduced the number of variables we need to optimize over, and we've implicitly created the lengths of, here, from whatever we get back from the optimization procedure over the C prime code, we're going to get a value of L prime m minus 1, and we're going to use that value to give us the lengths for L m minus 1 and L m. So in some sense, what Huffman does is it takes a minimization over m lengths, and it turns it into a constant plus minimization over m minus 1 lengths. And we keep doing this, and eventually it's going to turn into a minimum. Each one of these are going to be constants. It's going to be a minimization over 2 lengths. And when you only have 2 lengths, that's easy. We just assign each length to 1. Because we can do that. And Huffman preserves the 3 stated properties at each stage. And we reduced it down to a length 2 code, which is obvious to optimize. And we ensure that optimality is preserved at each step. Because the properties of the code, we've never violated these 3 properties. So we're guaranteed by that theorem that we just proved that there exists a code that's optimal with these properties, as long as the other thing. So therefore, we've proven now that the Huffman coding procedure is optimal. It's an optimal coding procedure, amazingly enough. Now the Huffman coding is a symbol code. We code one symbol at a time. So is Huffman optimal? But what does, in some sense, optimal mean? For a symbol code, each symbol n in the source alphabet must use an integer number of code words. And for d-adic distributions, the ones that are basically have probabilities 2 to the negative some integer, that is right. But in general, we could use an extra 1 bit on average. So for example, and this is that bad example. I think there's one missing 9 here, but it's another bad example. Huffman does something smart here, though. Basically, it only uses 1 bit for each thing. But in general, again, there's going to be rounding error. So we still haven't avoided the long block error. And so the Huffman code still take advantage in the non-d-adic case. Can take advantage of long block lengths. And we've already talked about this. Now the other thing, we might say, well, what's the problem with long block lengths? Is this a problem? Well, can we easily compute this? That's what I want to sort of talk about. In general, we need a very, very big table. If A is the alphabet size here, then we need a table of size A to the n just to store these probabilities. And in general, it's really hard to estimate these sorts of things. The reason is that even if we were, there's a sort of training data, there's an amount of data that you could maybe use to train this probability distribution. This is a massive joint probability distribution. For all these different probabilities. And in any given finite sample size, many strings just won't occur. And this is, given all of the data on the internet, this is still the case, for example, in search engines. I can ask you, for example, to try to go to a search engine, identify a valid English phrase that's never before been written on the internet or by anybody. I've recently done this. I mean, I don't know if this is a short one, but this is a pretty long one. But the phrase is, dogs ate banks on the river. So I went, as of Monday, October 28th, 2013, I went and I just dropped my pen. Google doesn't find any hits for that phrase. Now, your exercise is to actually find shorter ones. The point of this is that if we were to be given a training data set when n is large and we want to estimate this thing, most of the probabilities of this table would be 0. And that doesn't mean it really is 0, it just means that we haven't encountered it yet. And so what people usually do when they do density estimation is some sort of smoothing. And smoothing, it turns out to be very similar to the language model problem in natural language processing. So when we use long block lengths, we're going to, whether it's coding or something else, we're going to have to do this thing. Now, Huffman has the same property as the Shannon code, that basically Huffman is optimal integer, and it's basically at most 1 bit of penalty. And bigger block sizes help, because when we divide by n, this 1 over n here goes to 0. So we haven't really avoided that problem. We still, even with Huffman, even though it's optimal in terms of the integer lengths, it's not optimal in terms of the real valued lengths, and so we potentially could still be paying this penalty symbol, which could be severe when the entropy is small. So, and the same other issues with block codes, the latencies, and so on and so forth. Okay, so I think what I'm going to do now is stop this first half of the lecture and upload it to YouTube, and we'll do Shannon, Fano, Elias codes a little bit later, maybe, and I'll upload that again. So I guess there is going to be two lecture 10s, or maybe I should make this lecture 10 and lecture 11. I don't know. But in any event, we're going to stop now. And please, if this doesn't make sense, watch the video again, and I will see you soon, or talk to you soon.